Hello everyone. So today we're going to go over section 8.1, Reciprocal, Quotient, and Pythagorean Identities. So first things first, every single one of the identities that are in these boxes here, these will be provided on any test on a formula sheet. So they are not needed to be memorized. However, if we look at this identity here, cosecant x is equal to 1 over sine x, we can rewrite this identity as sine x is equal to 1 over cosecant x. That will not be given on a formula sheet. That is something that we'll need to derive on our own, on a test or on a quiz. Likewise, cosine x is equal to 1 over secant x is also not going to be provided. And finally, tangent x is equal to 1 over cotangent x. That is something that needs to be derived as well. Another piece of information that will not be necessarily given is the restrictions concerning individual identities. For example, here we have 1 over sine x, and of course that only works if sine x is not equal to 0. Okay, so that is implied in the definition. Same thing with here as cosine x cannot be equal to 0. And generally, the restriction just boils down to those two in general. So again, tangent x is equal to sine x over cosine x. So of course, cosine x cannot be 0 here. And for cotangent x, that is cosine x divided by sine x, and here we have sine x cannot be equal to 0. Now, those restrictions can be further elaborated upon. So let's say we have cosine x cannot be 0. Of course, the cosine x is equal to 0 if the angle is either pi over 2 or 3 pi over 2. So that means that x cannot be equal to pi over 2 plus pi n, where n is an integer. Also, for sine x to be not equal to 0, then x is not equal to pi n, where n is again an integer. Since if the angle is 0 or pi, then sine x would be 0. And if sine x is cannot be equal to 0, then x cannot be pi n. So it's very similar to the cosine x restriction. Okay. So the first two categories of identities, that is the reciprocal identities and the quotient identities, are familiar. The next one is a new item, and that is the Pythagorean theorem and then the identities to go with it. So here we have sine square x plus cosine square x is equal to 1, which is the one that's usually given. And the other two are tangent square x plus 1 equals to secant square x, and also 1 plus cotangent square x is equal to cosecant square x. And let's look at where that identity comes from. So starting with the first one, which is sine square x plus cosine square x equals 1. So consider our equation for a circle y squared plus x squared equals r squared. So what we can do is divide all three of these by r squared. In the first step, so the first term can be rewritten as y over r all squared. The second term will be x over r all squared. And finally, r squared divided by r squared gives us 1 on the right-hand side. Recall also the definitions of sine and cosine. So sine theta is equal to y over r, and cosine theta is equal to x over r. So from there, what we can do is replace y over r in the first term with sine theta, and the second term will be replaced by x over r can be replaced by cosine theta, and then of course is equal to 1 on the right hand side. And of course the square on the outside the parentheses can be rewritten, so we have sine square theta in the first term, and then cosine square theta for the second term, and that's equal to 1. So that's how we can derive this identity here. Now the other two identities in the same box can be derived from the first one. So let's look at, for example, what happens if we divide all three terms in the original identity by cosine square theta. So again, we are going to divide all three of these by cosine square theta. So let's write it this way. And then cosine square theta on the right-hand side as well. So the first term, sine square theta divided by cosine square theta, gives us tangent square theta. And then the quotient of cosine squared theta divided by cosine square theta is just 1. And on the right-hand side, we have the reciprocal of cosine square theta, which of course is secant square theta. So that's how the second of the identities can be found or derived. And finally, the last one, same kind of idea, but this time around, we're going to divide every term by sine square theta to achieve very similar results. Okay, so we can divide all three of these by sine square theta. The first term will, of course, become just 1. The second term will be cotangent square theta. And on the right-hand side, we're going to have cosecant square theta. So that will be this identity here. So again, 1 plus cotangent square theta, and then is equal to cosecant square theta. And of course, the other stuff that we would do is to replace thetas with x, and the identities will look the same. Another important piece here that should not be neglected is the idea that in the second expression, because it contains tangent and secant, then here cosine x cannot be equal to 0. And in the third expression, since we divided every term by sine square theta or sine square x, then this is sine x cannot be equal to 0, which of course can be referred back to the restriction that we found earlier. Okay, so these trigonometric identities are trigonometric expression, not functions, that are true for all permissible values. So it's important to identify the restrictions like we did earlier. And we can verify these trig identities by substituting specific values into them, but it doesn't in any way prove the identity, because just because identity works for a specific value, it doesn't mean it works for all permissible values. So that's a little bit different. But for right now, what we're going to do is just verify some identities numerically by substituting in pi over 6 as x, and see what happens. So in this first case here, we have sine squared, and then we'll substitute in pi over 6, and then cosine squared, and we'll substitute in here pi over 6 as well. And it should be equal to 1 on the right hand side. So sine pi over 6 is equal to 1 half. So the first term becomes just 1 half squared. Cosine pi over 6, of course, is root 3 over 2. So we have root 3 over 2 squared. And it should be equal to 1 on the right hand side. So of course 1 half squared is a quarter. Root 3 over 2 squared is 3/4. And the sum of those two is equal to 1. So the identity has been verified for pi over 6. Likewise, on the right hand side, tangent square pi over 6 plus 1 is equal to secant squared and then pi over 6. So tangent square pi over 6 we know is 1 over root 3. Again, both these questions are done using the special triangles. So we know on the right hand side, secant square of pi over 6 we're just going to be the reciprocal of the term we already found. So this is going to be 2 over root 3 all squared. So this would be 1/3 plus 1 is equal to 4 over 3. So of course that works as well. Now for these two versions of the Pythagorean identity, because we derived them using the equation of circle, we know that they work. So there's usually no need to verify them. It is just to these two examples is just to show how that question would be done if we are asked to verify potential identities. Okay, so given the identities that we have, we can simplify some trigonometric expressions and also find their restricted values. So in this first example here, we have simply sine x over cosine x. If we are to rewrite it as a single term, then of course we know that this is just equal to tangent x. Now, what is also important here is what are the restrictions. So we know that since cosine x is in the denominator, it cannot be equal to 0. And as we saw earlier, if cosine x cannot be equal to 0, then x cannot be equal to pi over 2, 3 pi over 2, and so forth. And it generalizes to pi over 2 plus n pi, where n is an integer. So that is our restriction for this expression. So that is to say, sine x divided by cosine x is equal to tangent x, provided that x is not equal to pi over 2 plus n pi for some n, where n is an integer. Okay, let's look at a second example here. So this one is a little bit more involved because cotangent can be first expanded to say cosine x divided by sine x, and this will be all over cosine x. Okay, so that means not only do we have cosine x cannot be equal to 0 on account of the denominator in the original expression, we also have to contend with the fact that cotangent x is equal to cosine x over sine x, so we have a denominator of sine x as well. So sine x also cannot be equal to 0. So now this first expression has a restriction of x cannot be equal to pi over 2 plus n pi, where n is an integer. And the second expression here says x cannot be equal to n pi, where again n is an integer in both cases. Now, if we were to take a step back and think about this in terms of the angles, this will cover 0 and pi, and the expression on the left-hand side will cover pi over 2 and 3 pi over 2. So every integer multiple of pi over 2 is covered by the combined expressions. So if we have a question where cosine x cannot be equal to 0 and sine x cannot be equal to 0, then the combined restriction is actually just x cannot be equal to pi over 2n, where n is an integer. Okay. And that is the case for example B. So if we have cotangent x divided by cosine x, then x cannot be integer multiples of pi over 2. Okay, let's continue simplifying this. Of course, here the factors of cosine x will be eliminated in both parts. So this expression simplifies to just 1 over sine x. And as we know, 1 over sine x is equal to cosecant x. Again, so what we want to do is generally want to rewrite the expression in terms of sine and cosine, figure out what the restrictions are, and then simplify the expression afterwards. So let's look at another one here. Once again, the first step is to rewrite this in terms of just sine and cosine. So tangent, of course, is equal to sine x over cosine x. In the denominator, we have secant x, which of course is 1 over sine x. Sorry, 1 over cosine x. Sorry about that. And then sine x is just sine x. And we have both sine x and cosine x in the denominator. So the restriction in this case is that neither cosine x nor sine x could be 0. And we have the restriction x cannot be equal to pi over 2n, where n is an integer. So from here, of course, the sine x will be eliminated, and then also the 1 over cosine x will be eliminated as well. So this expression actually reduces to just 1. And that is to say, tangent x divided by secant x times sine x is equal to 1 if x is not equal to integer multiples of pi over 2. Okay, so last one is a bit trickier. So first of all, we have a denominator, 1 minus cosine square x, which is not just sine x or cosine x. It's a little bit different. So let's consider what happens here. We have 1 minus cosine square x cannot be equal to 0, which means 1 cannot be equal to cosine square x, which means if we square root both sides, then cosine x cannot be equal to positive or negative 1, which means x cannot be equal to integer multiples of pi. If x is equal to 0, then of course, then cosine x is equal to 1, and that's not permissible. And likewise, if x is equal to pi, then cosine pi is equal to negative 1, and also that's not a permissible value. So of course that can be extended to include all integer multiples of pi, so x cannot be n pi, where n is an integer. Okay, so the other important piece here to simplify this expression is to consider the Pythagorean identity. So we have sine square x plus cosine square x is equal to 1. And so if we subtract both sides by cosine square x, we know that sine square x is equal to 1 minus cosine square x. And it is this corollary, if we will, of the Pythagorean identity that we can use to work with this question. So here we can rewrite the expression as sine x cosine x all over sine square x. Okay, so from here, the sine x will eliminate one factor of the sine x in the denominator. So this just simplifies to cosine x over sine x. And we are just going to get cotangent x. And that's it. And of course, x cannot be integer multiple of pi. So the tricky part of these questions is there. It just says to simplify the expression. So it's sometimes difficult to tell if we are done the question. However, in the latter parts of this unit, we are trying to make trig identities to be equal to each. Sorry, trigonometric expressions to be equal to each other, so we know um, what we're working towards. So those questions are easier because we know when the question ends, but they're more complex because there are more trig identities to work with. Um, anyways, that's later on in this unit. So one more thing. So we can also verify trigonometric identities graphically using technology. So again, similar to substituting in values, is not always a way to go. But just for an example, if we want to show that here we have secant x is equal to tan x over sine x, we can use a graph for that. So we'll probably plot it on Desmos, let's say something like this here. So the function that is in red here, this is y equals secant x, and in blue, here we have y equals to tangent x over sine x, and as we can see, the two graphs overlap each other perfectly, so we know that they're equal to each other, at least from what we can see. But the emphasis on this unit is going to be on proving trig identities algebraically. But that's it for today, so thank you for listening.